This is a video presentation for INC281 Capstone Final Project 2021. For the project, we designed and simulated a monitoring system for a hydroponic medical marijuana farm. Yes, I said medical marijuana. The system utilizes IoT or Internet of Things and automation to maximize productivity of the farm and guarantee the best quality of the produce. Giving a teaser of some parts of our report, I will be briefly going over just the overall idea of the system and the hardware components that belong to it. The farming system itself is based on growing hydroponics, a method of growing plants without soil, using mineral nutrient solutions in an aqueous solvent to directly nourish the plants. According to the diagram, you don't see any soil that is in the system. That is because the plants are instead being fed with water and nutrients mixed inside of it. In the system, sensors and actuators are present to assess and ensure optimal conditions for the growth of our marijuana. These systems and actuators enable temperature control, humidity control, light intensity control, pH control, water pump control, air pump control, water level detection, and buzzer alarm for the motion detection sensor, which all of these could be monitored, accessed, and controlled through the dashboard of our website. Now, when implementing the sensors, it is important to know that the voltage input into the microcontroller, this is the microcontroller, needs to be between 0 to 3.33 volts. So when the sensor gives out a certain voltage, it will have to be 0 to 3.33 volts in order to be able to be inputted into the node MCU. With this, we have to be able to convert the signal voltages from some sensors to make it 0 to 3.33 volts. The sensors we designed these circuits for were the temperature sensor, light intensity sensor, and the humidity sensor. So this is the steps and theory on how to design a circuit. And okay, this is the temperature circuit design. This is the light intensity circuit design, which is the simplest one out of the three because it only needs voltage divider. And lastly is the relative humidity circuit design, which is the most complicated out of the three because the V offset is a non-zero value and it needs another inverting amplifier circuit in order to invert the signal to get what we want. The calculations and theories and diagram are all in here, and we've additionally added a functional flow block diagram. So to show you, this is a functional flow block diagram, which gives visual understanding on how the sensors work and communicate with the web app. That is all for the overview and summary of the sensors and how we implemented them to work with the microcontroller. We will now move on to the web page, simulations, and code.
I will now be showing you the web page application for farm. As you can see in this code, you right-click index, open with server. You can go to the home page. Display as follows. I will showing you each part of web page tab by tab. Our group have 5 tabs here. 1. About us. 2. Tribe. 3. Review. 4. Contact us. And 5. Highlight dashboard. I start with first tab, about us. The first tab is about us. If you click on it, it will direct you to the About Us section of the web page, which includes a short summary for what we do. If you click Read More, it will take us to all the page where the whole project is planned in the more detail in the standpoint, where we are trying to sell our concept to the reader. And if we click on Mali, we can go back to the home page. And the next tab is Type. It will direct the user to the type of medical marijuana our system goes. If you click on the picture or the underlined text, the link will take you to the Wikipedia page about plant for if the user wants to learn more. And I have 3 types of marijuana. And below, the section is What is medical marijuana? And it's also user who want to learn more, click for more info. And will direct the user to other website talking about medical recreational marijuana. If you want to back, you can click arrow. And the next tab is Review. The Review tab will direct user to customer review of our high quality plants. And the next is Contact Us. Contact Us will direct the user to a form where user can message the company to ask any question or order our products. And the lastly is the most important, is the Dashboard tab. If user click on this tab or go to Dashboard on the web page, it will direct user to other page where they can view the sensor data. All the sensor in the circuit can be monitored by the web application, and all actuator in the circuit can be controlled by the web page application. Right now, the simulation is not running, so on data show the graph, but my teammate has already game analog with the dashboard for you to see private list. And if you click on home once again, we can go back to home page. Therefore, the control and monitoring application can be run in a website browser.
Let's take a look at the JavaScript code behind the Pro Tools. So here first is the array that holds the object in from the button, push button, and the 6 variables here are the global variables declared for holding the temperature, humidity, light, temperature pulse width mode, humidity pulse width mode, and light pulse width mode. The new grid function here is used to create the grid, so we can add these objects to 2x4 grid. So the objects in our dashboard will look very neatly and easy to use. Next function is Psw function, which is switch button functions, and is consists of the 4 button here: water pump, air pump, bird detect, waterable danger, and the color will be this. And next is the plot temperature graph, which is only the background of the graph, not the line plot. So we have 4 plotter graph here for temperature, humidity, light intensity, and pH, which has different min and maximum value here. As you can see, the normal pH in our real life is between 0 and 14, for example. So we set the value in the plotter as 0 to 14. Next is the gauge to indicate the pulse-width modulation of the temperature fan, the humidifier fan, and the grow lamp, which have the ticks minor and ticks major to indicate the tick in the gauge. And next is the threshold. So we have the 3 threshold functions for the temp fan, humid fan, and grow lamp. So it will receive the value of 0 to 1023 from the ADC in the Proteus. And for example, here is if the value is more than 250 and less than 300, which is around roughly 25 Celsius, and lower than 30 Celsius, the temperature fan will have the pulse width modulation of 0.33 or 33%, and this temp PWM will show in the gauge, this gauge, temp fan, and the humidity threshold as well. So if the humidity is more than 70, or 70 is our optimum value for plant, the fan will only turn on for with pulse mode only 0.1, and if it's getting lower, which is not good for our plant, the fan will start operating more intense, and if it's very dry, the fan will operate at its maximum capacity. The lamp threshold is the special case because our plant need light that is more than 10k lux, and is around 15k lux, which is quite high and too high for our sensor to measure, because our sensor can only measure from 0 to 10k lux, which is the LDR. So if the light is lower than 10k, which means it's getting dark, the lamp will operate at its full capacity. And next is the set interval every 3 seconds to check if these value change. So if these values change every 3 seconds, the pulse width mode will change to whether higher or lower pulse width modulation in our analog components. And last is the main function here, which consists of every function we declared to put everything in the dashboard. And here is the set the time of 3.5 seconds to receive the value from ADC here, and add the point to the plotter first, which this value, and add the value here to the gauge temp. So so the gauge is going to be different for each here. Here is for temperature, here's for humidity, and here's for light intensity. And the pH has no components that connected to it, so we only show its graph here every 4 seconds. And the last one here is grid child, which is the grid function here we call. So we takes every object that declines the function into the grid. So these are our proto schematic circuits. Let's begin with the microcontroller part. So here we have 4 of the potentiometer that control the ADCs, but actually we don't use these 3 because it will be linked to our sensor, but the ADC0 here is for the pH meter because we cannot find the appropriate sensor that measure pH in the Proteus. So let's mimic this. Is our pH meter, and the 4 switch here, which is Psw3 is water pump, Psw2 is air pump, Psw1 is bird detect, and it will be a buzzer here, and Psw0 is water level danger. So let's begin with the sensor first. So we have 3 sensors here. This one is the temperature sensor, which consists of the LN35, which measure our desired range of measure is 0 to 100 Celsius, which output the 0 to 1 volts if the supply is 9 volts. But we want the input to ADC3 here. We want the value of 0 to 3.323 volts. So we will use the op amp to amplify the 1 volts maximum here into 3 volts, which DC gain of the op amp here is definitely 3.323 volts, and this max 1 over 4 here is for inverting the 9 volts here into negative 9 volts to be supplied to op amp here. Next is the light intensity sensor. We use the LDR here to be the resistor that detects the light intensity. So it's originally output 0 at 0 lux to 8.58 volts at 10k lux, with 9 volts supplied. And we use the voltage divider here to reduce the maximum 8.58 to 3.33 volts, and it puts it to ADC1. Next is the humidity sensor. This one is different because the minimum of the voltage output here is not 0, so we have to use the zero span adjustment circuit, which consists of 2 op amps here. We modify the output from HIS sensor here from 0.5 at 0% relative humidity to 2.58 volts at 100% relative humidity percent, and the output will be 0 to 3.33 volts. Next is the water pump, air pump, and the bird buzzer, which is the digital components. If the switch is on, the NOT gate will invert the 1 to 0 and trigger the relay here from this side to be here in this side, and the voltage from 24 volts will flow into our pump, water pump, and air pump too, and also the bird buzzer. But the bird buzzer will use the lower voltage here. As you can see, it uses only 12 volts. And the last thing is in our circuits is the lamp, which use pulse width modulation control to control the DC here. The pulse width modulation tree here will control the fan fan to reduce the temperature. The number 2 here will control the humidifier fan to increase the humidity in the farm. And the number 1 here is the grow lamp, not glow but grow. This is the lamp that used to grow the plants. Okay, let's take a look at the simulation. So first, the temperature here is 25 Celsius. The graph outputs 25 Celsius. Very accurate. The light intensity here is 10k lux, and here the graph for the light intensity, which normally at its maximum of the graph of 100 here. And next is the humidity sensor, which is 80% relative humidity here. And this is the graph for the humidity sensor. As you can see, at normal state it is 80%, but the fluctuation here, the error here, is caused from the communication problem in the virtual part between these here, the COM4 here, and my COM3 port. And the last ADC here is for the pH here. You can see that at around 54% of potentiometer, its output, it tells that our pH is around 7.5. And let's take a look at the digital switch here. So first, let's begin from Psw 0 is the water level danger. So if we press here, you can see that the red LED here is on, or we can hold it down. Okay, it's on. And Psw1 here is buzzer for the bird detect. It will, if it detects the bird, it will make the sound, loud sound, to scare the bird away. And the Psw2 is the air pump in our hydroponic farm, and Psw3 is the water pump. So let's turn on both. So both turn on already. Let's take a look at our water pump and air pump. As you can see, it's turned on and operating at its capacity. If we turn off, it's going to be slowly decrease here to 0. And next is we're gonna take a look at the graph before it's getting more error. So let's change the temperature to 40, for example. We change the temperature from 25 to 40. The graph will increase from 25 to 40 here. And as I said earlier, if the temperature increase, the fan will operate faster. Here you can see. So we can take a look at the command prompt. At pulse width number 3, the fan is now 0.6 or 60% of the pulse width modulation. So let's take a look. So here I wrote if the temperature more than 35 Celsius to around 40 Celsius, the pulse width modulation is going to be at 60%, which is correct. So you can see at 80% of the relative humidity, the fan will operate at only 10% of pulse width modulation, which is corresponding to our code here, and the command prompt here, which sends 0.1 to the pulse width number 2, and our fan will just slowly increase its power. You can see that the temperature fan will increase faster than the humidifier fan. And the last one here is the grow lamp, which is 99% of the pulse width modulation, because the light intensity sensor is at 10K, which is considered quite dark, which is not very suitable for our plant. So we turn on the lamp at its full capacity of pulse width modulation.
To conclude, users could fundamentally implement this smart farm to cultivate other hydroponic plants if they wish to do so. This system is not only for growing medical marijuana. Users would only have to modify the thresholds in the code of the sensors according to the plant species' optimal conditions. That way, the farm will run just to take care of that plant. That's it for our presentation. For more detailed information about the project, check out our report. We hope you enjoyed it. Thank you and take care.